I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
A choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Happy Halloween! I can't wait for the costume party tonight.
Me either. I think everyone will love my costume. I made it myself.
What are you, a zebra?
No.
A referee?
No.
Then what are you?
The Doppler effect. Can't you tell?
No, Nick, don't do this. Don't go as a Doppler effect. No one will know what you are.
Yes, they will, Bailey. Everyone knows what the Doppler effect is.
Okay, Nick.
Look, I know that not everyone is a rocket scientist, but this is obvious. The Doppler effect is at the basis of physics knowledge.
Okay, well, let's say that no one knows exactly what the Doppler effect is. How are you going to describe it to someone at the party when they ask what it is?
I'll say that the Doppler effect is the change in frequency of a wave for an observer moving relative to a source of sound when the source of the waves is moving towards the observer. Each successive wave crest is emitted from a position closer to the observer than the previous wave. Therefore, each wave takes slightly less time to reach the observer than the previous wave. Hence, the time between the arrival of successive waves crest at the observer is reduced, causing an increase in the perceived frequency. While they are traveling, the distance between successive wave fronts is reduced, so the waves bunch together. Conversely, if the source of waves is moving away from the observer, each wave is emitted from a position further from the observer than the previous wave, so the arrival time between successive waves is increased, reducing the perceived frequency. The distance between successive wave fronts is then increased, so the waves spread out.
Okay, well, for people that speak English, I think that might be a little hard to understand. I think you might need to demonstrate it instead of just explaining it.
Meow.
Well, that was nice, but maybe we should come up with a better way of showing people what exactly the Doppler effect is. Here, you can use my lucky tuning forks. You can carry them with you tonight to show everyone what the Doppler effect really is.
You're right, yes. That would get me all the chicks.
We should compute just how much frequency a person at the party will hear if we are walking towards them with the fork at a certain speed. The equation is frequency that the person will hear equals the speed of sound divided by the speed of sound minus speed of us moving with the fork to the person times the frequency of the tuning fork.
How many hertz is your lucky tuning fork?
It is 512 hertz.
We can substitute 512 into the equation for the frequency of the tuning fork.
Yes, and the speed of sound depends on the temperature. The equation for that is V equals 331 meters per second times 0.6 meters per second per degree Celsius times the temperature outside.
Okay, and if we can move at a steady pace of 1.4 meters per second towards a person at the party, then we can substitute that in for speed of us with the fork moving to person.
Exactly, and if we compute this correctly, which I obviously will, the frequency that the person at the party will hear should be higher than 512 hertz, because since we are the source of the sound and we are moving towards the person, they should hear a higher frequency than the actual frequency that the fork is emitting.
Yay, let's get computing!
This is the equation for the Doppler effect when the source of sound is moving towards the detector. So f sub d is the frequency that the detector will hear, which in this case is the person at the party, is equal to v, which is the speed of sound, divided by v minus v sub s, which is the speed of the source of sound, which in this case is Nick walking with the tuning fork, times f sub s, which is the frequency of the source of sound, which in this case is the 512 hertz. This is the equation for the speed of sound, v. It's 331 meters per second plus 0.6 meters per second per degree Celsius times the temperature outside, which in this case was 75 degrees Fahrenheit, which equals about 24 degrees Celsius. And when you substitute everything into the equation, including the 1.4 meters per second, which is the average walking pace of a human being, you get 514 hertz, which is the frequency that the detector will hear, which is the frequency that the person at the party will hear, which is 2 hertz higher than the actual frequency that the tuning fork emits.
Awesome, so at the party, I'll carry around your lucky tuning fork and use it to explain the Doppler effect for anyone that doesn't know what it is, and I can tell them that even though the actual frequency emitted by the tuning fork is 512 hertz, they're actually hearing 513.4 hertz because I'm walking toward them.
Yes, exactly. Now that I think about it, you could have just explained it to them in this way. It's like when you're pulled over in your car waiting for an ambulance to pass. When the ambulance is approaching you, the frequency of the siren gets higher and higher. When it passes you, the frequency of the siren gets lower and lower until it is so far away that you don't even hear it anymore.
That may be easier to understand, but it's not as cool.
Hey Nick, you look awesome. I've always wanted to be a zebra for Halloween.
Look, Bailey, come over here. Let's see if this works. I'm not a zebra. I'm the Doppler effect. Would you like to see exactly what the Doppler effect is?
Sure.
You're going to hear a frequency of 513.4 hertz, but the actual frequency emitted by the tuning fork is 512 hertz. Cool, huh? Maybe I should have just went with the clown costume instead.
Here, doing it right.
Hey, on this GoPro when we're filming. Just come on, let's go. Is recording.
Oh, start over.
Me neither. Wait, it's supposed to be me either.
Start over. You should keep it tight on the fur. Okay, start over.
Conversely, if the source of waves is...
Much together is the end of a sentence. You can't keep reading.
Well, there's no freaking
Yes, there is. You
period.
just can't see it.
Okay.
Start over.
While they are the equation for the frequency. Yeah. Okay.
Stop.
Yeah. Yay is gay. Yay, let's get computing.
You have to get excited about it.
Yay, let's get computing. That may be easier to understand, but not as cool.
You have to get excited about it.
That may be easier to understand, but it's not as cool.
No, it's not cool.
That may be easier to understand, but it's not as
No,
cool.
I know what you should say.
That may be easier to understand, but it's not as cool.
There you go.
The Doppler effect.